Let's start the video with problem number 62, which involves simple harmonic motion, and then we will go to some other problems involving theory and examples. In this one, the position of a body, of a moving body of course, is given as a function of time. So S is the position and T is the time. S equals sin t plus cos t. If you draw the graph of this function where you consider this as your y variable and t as your x variable on Desmos graphing facility, you will see that the graph is like a wave. So the motion this equation is describing is actually simple harmonic motion. What is it that we have to do here? Here S is in meters and t is in seconds. Okay. We have to find the body's velocity, speed, acceleration and jerk at time t equal to pi over 4 second. So let's just calculate these things. We just have to differentiate again and again. So we first find velocity, acceleration and jerk by successive differentiation. First we differentiate position with respect to time, that gives us velocity. So sin t will give us cos t, means the derivative of sin t is cos t. The derivative of cos t is minus sin t. So this is the general velocity as a function of time. If you put some specific time value here, you would get the body's velocity at that instant of time, because this is instantaneous velocity, not average velocity. In our case, we are of course going to put t equal to pi over 4. But let us first calculate the other quantities. Acceleration is the instantaneous rate of change of velocity with respect to time. So you differentiate this once more. Differentiating cos t, you get minus sin t, and differentiating sin t, you get just cos t. So minus cos t. So that is our general acceleration. And then jerk is the rate of change of acceleration with respect to time. So you differentiate this once more. Minus sin t gives you minus cos t, and differentiating cos t you get minus sin t. So minus cos t gives you plus sin t. So these are the three quantities. And now we will actually calculate what we have been asked to calculate. So first we calculate the velocity when the time is pi over 4 second by simply substituting t equal to pi over 4 here in the general velocity formula. So the velocity at that time, because it's a function, so we can use this notation. The value of the velocity function at that time instant is cos pi over 4 minus sin pi over 4, both of which are 1 divided by square root of 2, and so the value is 0 meter per second. Do not forget the unit, okay, because it's given in the statement of the problem that S is being measured in meters and t in seconds. So there is no velocity. At that instant, whatever simple harmonic motion the body is undergoing, momentarily it is stopping at that instant and then continuing. And that implies what? The absolute value of velocity is speed, because we have to calculate speed also. That is also 0 meter per second. And next comes acceleration. So we evaluate A at pi over 4. This one is minus sin pi over 4 minus cos pi over 4. That means minus 1 over root 2 minus 1 over root 2. So minus 2 times root 2 or minus root 2 meter per second squared. Okay, not meter per second, because this is acceleration. And next comes jerk. So the jerk at pi over 4 second would be minus cos pi over 4 plus sin pi over 4, which ultimately is 0, just like the velocity is 0. Meter per second cube, okay, because it's the rate of change of acceleration, and acceleration already has this unit. So the rate of change of that means, again you are dividing by time. I mean, I'm talking about the unit. So there is no abrupt change in acceleration either in magnitude or direction at the time instant t equal to pi over 4. So there is no jerk. So that's the solution. And next let us see problems involving theory and examples. So next we have problem number 64. Is there a value of b that will make this function continuous? Continuous at x equal to 0, differentiable at x equal to 0. Give reasons for your answers. So let's now see what the function rule is, what its definition is. For a negative real number input x, g of x equals x plus b. We don't exactly know what b is, in fact b can be anything, and the question is that for what value of b this function will be continuous at x equal to 0, differentiable at x equal to 0. These are two different things, okay? And when our input x is a non-negative real number, that means it's either positive or equal to 0, then the output is cos x. So let us first see if there is any value of b that will make this function continuous at 0. So for continuity of g at x equal to 0, we separately calculate the left hand limit of g at 0, its right hand limit at 0, and its value at 0. So what is the left hand limit of g at 0? Because in this limit x is approaching 0 from the left side. So x is a negative real number. I mean, as a variable it's a negative, it takes on negative values. So that is why, according to the definition of the function g of x would be equal to x plus b, because that's what happens on the negative side of the x-axis. And when x approaches 0, x plus b approaches b, so the left hand limit is b. And when you consider the right hand limit, this time g of x is equal to cos x, because that's how the function has been defined. And we already know the limit of cos x at x equal to 0. Here we are talking about the right hand limit, but actually the two-sided limit of cos x at x equal to 0 is cos 0, because cosine function is continuous at x equal to 0. Actually it's continuous everywhere. So in particular the right hand limit also would be equal to 1, which is equal to cos 0. But note that when x is 0, then also cos x is g of x. So g of 0 is also cos 0. So that means in order to have continuity at x equal to 0, the left hand limit b should be equal to the right hand limit, which is already equal to the function value. That means b has to be equal to 1. That is the only value of b which makes this function continuous at x equal to 0. Next comes the question of differentiability at that point. Suppose that the function g is differentiable at x equal to 0, and we want to see what we get from this supposition. Do we get b? Do we get some specific value of b which will come out as a necessary condition of differentiability? Let's see. Now note that if a function is differentiable at some point, then obviously it's also continuous at that point. We already know that differentiability implies continuity. And just now we saw that only this value gives us continuity. So that means now we have to take b to be equal to 1. That's the only possible value. But then you may say that, okay, so then that itself determines b. What else are we doing? Why do we need to then do further calculations? That is because we haven't investigated what is going on fully. Let us also see what the other consequences of this supposition are. Alright. Now if we calculate, because we are saying that it's differentiable at x equal to 0, so if we calculate the one-sided derivatives, left hand derivative and right hand derivative, they have to agree, they have to be equal at x equal to 0. The left hand derivative at x equal to 0 is of course this, where you have your usual difference quotient. Ideally you should write g of h plus 0. In general, you write x plus 0 if the differentiation is happening at x. But here 0 plus h because the point is 0. So I haven't written 0 here. G of 0 plus h minus g of 0 divided by h, as h approaches 0 from the left side. That's why you see this little minus. Okay. Now h here is negative because h is approaching 0 from the left side of 0. And accordingly, if you go back to the definition of the function g, it will be what? G of h will be h plus b, and our b is 1. So that's how we have h plus 1. Minus g of 0 we have already seen, it is cos 0, which is 1 divided by 8. So if you cancel 1 and minus 1, and then if you cancel h, you are left with 1, the constant function 1, whose limit of course at any point is 1. So the left hand derivative at 0 is 1. And what is the right hand derivative? The right hand derivative similarly is this. The only difference is that here h is approaching 0 from the right side. Now h is positive, and because h is positive, g of h is cos h according to the definition of g. G of 0 as before is 1, and you already know this limit. You know it like this: limit h tends to 0 cos h minus 1 divided by h. You know the two-sided limit, and its value is 0. So in particular, the right hand limit is also 0. But then what are we getting? The left hand derivative is 1 and the right hand derivative is 0, which immediately tells us that no, the function is not differentiable at x equal to 0. So you see that you have, your supposition ultimately contradicted itself. So that means the supposition has to be wrong. So there is no value of b that makes the function differentiable at x equal to 0. In fact, if you use this value of b, that b is equal to 1, and you draw the graph of the function on Desmos again, you see that at x equal to 0 there is a sharp corner. What was the definition of g? On the left side it was x plus b, which now is x plus 1. So the graph is a straight line on that side, and then it is the cosine graph. So that point where the transition is happening, there is a sharp corner, and we do not have any unique tangent at sharp corners of any curve. That is why it's not differentiable at x equal to 0. Let's see another one. Next we have this number 66, a very interesting one. We have to calculate the 725th derivative of sin x. Suddenly it seems impossible, but there is a pattern. Let's see. And the pattern is this. Let us first calculate the fourth derivative of sin x. You differentiate sin x once, you get cos x. You differentiate once more, that means that will give you the second derivative of sin x. So that means you are differentiating cos x. So you get minus sin x. Differentiating once more gives you the third derivative, where minus of course stays minus, and differentiating sin x you get cos x. So this one is minus cos x. And once more if you differentiate, you get the fourth derivative. Differentiating cos x you get minus sin x, but already there was a minus. So you get sin x back. That means differentiating sin x 4 times has no effect on the function. You get the function back. This implies that differentiating sin x any 4k times, where k is any positive integer, also won't have any effect. Any effect means it won't change sin x. We will get sin x back. If this seems a little difficult to understand, think of it this way. What will you do after having this to calculate the 8th derivative of sin x? You will keep on differentiating again. First you find the 5th one, then the 6th one, 7th one, 8th one. So all these things will come back in that same pattern and you will again get sin x. So like that, 8 times, 16 times, 12 times. So all these things are ultimately going to give you sin x back. But how does that help us here? We have to find the 725th derivative of sin x. Let's see. So we note this identity, 725 equals 4 times 181 plus 1. So basically we divided 725 by 4 and this is the quotient and this is the remainder. So then how can we write this 725th derivative of sin x? We write the 4 times 181, that derivative of sin x, and then differentiate it once more because of this plus 1. So that will ultimately be d725. But this is sin x because the number 4 times 181 is of the form 4k. K here is 181. So this is sin x and then you differentiate that and you get cos x. So the 725th derivative of sin x is cos x. And let's just end the video here itself. Other exercises are also there which mainly involve graphing these functions. So we will see how many of them we will do before moving on to the next section. So see you next week with new things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.